Hello everyone, my name is Michael Omar and I will be making a presentation on research on developing some effective machine learning algorithms for detecting and forecasting risks and flood areas on maps. I want to use this opportunity to thank my supervisor, Professor Chengting Gan, and also Professor Nguyen Langzang for their support while doing this research. Uh, the table of contents contain four aspects of the research work that I want to briefly give an overview of the work. So I have introduction, the methodology, the experimental result, and then the conclusions, which indicates the findings of the work. Without wasting of time, we dive into the uh, introduction. Now, the importance of groundwater quality, it is critical foundation for environmental research. And we know that good water provide sustainability for the environment, provide good economic impact. However, poor water provide ecosystem disruption and also habitat loss and also provide public health risks. According to World Health Organization, over 2 billion people lack access to safe drinking water, and also contaminated groundwater causes waterborne diseases. And so if we look at the chart, pie chart by the right, which indicates percentages of freshwater availability according to research by Mishra et al., shows that there is a degradation of groundwater freshwater and groundwater availability across the globe. And so there is a need for securing and providing safe ground for groundwater as a natural resource. I will quickly talk about the overview of the research topic. And so these slides provide an overview of the topic, which is centered on enhancing the accuracy and the efficiency of machine learning models for groundwater quality classification and forecasting, specifically through the use of convolutional neural network and geographical information system. So as we can see, step one is classification of groundwater quality, where we start by imputing groundwater features. We begin by gathering physiochemical properties, data of the groundwater such as pH, temperature, and chemical concentration. These data form the basis for the classification. In steps two, we have the CNN model. So the collected data is processed using convolutional neural network. This is a type of a deep learning model designed to capture spatial patterns in data. And this allows for efficient classification of groundwater quality into different categories. So where we have the categories classified as either good, bad, and poor. Now, the next steps, which is steps two of the model mapping with GIS. So in these layers, we get the coordinates, that's the geospatial location data, and then integrate this data into GIS systems. And we now, at the last layer, we combine and we provide the classification results and coordinates locations of those well points, and then we visualize them on the map for better decision making. Now, the motivations and significance of the research problems. Now, motivation, we all know that the increasing global need for sustainable groundwater management is required. And also, traditional methods of water quality assessments are limited and time consuming, and they are expensive. Now, the significance of the research shows that groundwater is vital for drinking and also for agriculture and for ecosystem health. So now, contaminated groundwater leads to waterborne diseases and environmental degradation. And then for the research problem, the current groundwater quality assessment methods lack real-time capability. And so there is a need that we have to provide a hybrid AI models that can enhance accuracy and efficiency of these processes. I will quickly discuss about the background of the literature of the research work. Now, This slide highlights the limitations of traditional methods used in groundwater quality assessments. So the classical method in the first box, we see that the methods for assessing water quality typically involves laboratory-based procedures such as manual sampling and water quality index calculations. Now, challenges with traditional methods, as highlighted in the second box, is that they point out some of the major drawbacks. These methods are time-consuming and expensive, requiring a lot of manual efforts to collect and process the data. It is also labor intensive and subjective to slow and prone to subjectivity result, and also lack real-time monitoring. Now, in the other part, we also have the machine learning models after seeing the drawbacks of the traditional methods and how they are being used. So the machine learning methods also outlined the benefits and some of the challenges that are in these models. So key benefits, ML models, they excel at handling large complex data set, and they can provide real-time monitoring, which is crucial for timely decision making. And also some of the challenges that we find with these models are overfittings. They may perform well on training data, but they can struggle with generalization on unseen data. We can have a problem of interpretability because the complex nature of models like the CNNs can make it difficult to explain prediction clearly. And also computational complexity. The models require significant computational resources, especially for training deep neural networks. An overview of existing research and some methods that are available. So these slides provide an overview of a few existing studies on groundwater classification, their methodologies, and the limitation of each. So for example, the research by Kudio et al., the methodology used there was random forest and XGBoost for classification. They achieve a 97% accuracy for classifying water quality in urban areas, but the limitation of the research is they lack spatial data for visualization of the work and for a larger region. Then we have methodology by Zaga et al. So they combine light GBM, extra trees, gradient boosting. However, their method is based on the irrigation water quality index. So it is only limited to irrigation quality and dependent on also future selection. Then the last methods, groundwater classification, that uses deep learning, CNN and GIS groundwater classification, which provide real-time visualization of groundwater quality, but the limitation is that this requires GIS integrations for data, for spatial data. So the slides highlights the strengths and the limitations of each study, showing progression in using machine learning and GIS for groundwater. Now we have some comparison of some related work relating to machine learning. So it's just, we have the hybrid CNN GRU model that was developed by MKJ et al. So model use wavelength transform. The key feature was to enhance prediction accuracy by integrating multiple techniques. And they receive high performance precisions with light GBM. There's also a machine learning based water quality classification that use adaptive boosting, KNN and SVM. The key features is to utilize various machine learning algorithms for robust classifications. And then understanding the efficacy of UNet and vision transformer. This model uses LBoost fusion model. So the key feature was to predict groundwater quality risks in Odisha. And so the performance, it outperformed an FNO model in accuracy and efficiency. So these are a few comparison of related work. So challenges, gaps, and modern solution. So, bridging the gap between AI-powered classification and geospatial visualization for enhanced understanding, monitoring, and management of groundwater resources, we have to look at the traditional concept where we stated clearly that it is limited uh, accuracy. It has manual feature selections and also basic pattern recognition. So for limited accuracy, the methods often lack the ability to provide precise classifications. For manual features, they need to be selected manually, which can be error prone. And also for basic pattern recognitions, this method only recognizes simple patterns, limiting their effectiveness. And then for the moving into the DL and ML groundwater quality classification, we have improved accuracy, automated features, and learning complex pattern recognition. So we stated that improved accuracy models often offer much higher accuracy in groundwater quality. Automated features, they can automatically learn the relevant features without human inputs. And for complex pattern recognitions, they can detect complex patterns in data that traditional methods cannot. Now, to address the research gap, we look at integration of spatial CNN-based classification with the GIS mapping. So in summary, the slides highlights the advantages of DL methods over traditional techniques and also emphasize how the integration of spatial CNN can improve groundwater classification. So we have a research question that we ask, how can machine learning models improve groundwater quality classification? How can hybrid models such as AI, LGBM, PSOSCN enhance accuracy and scalability? And how can GIS integration help with spatial mapping of water quality? Now, in order for us to answer these questions, we set up the problem statements. So first, we're looking at spatial data integration and classification. Now, the objective is to classify groundwater quality as excellent, good, poor, and bad, and then to optimize the SCNN hyperparameters with particle swarm optimization. We provided a mathematical formulation for our data set. Input data structure was given as an X. For optimization, PSO optimization, we provided an objective function. And then for the model, running the SCNN with PSO optimization. So the innovative context in this problem statement is combining spatial convolutional neural network with particle swarm optimization for enhanced groundwater quality. The second problem statement is to classify groundwater features into distinct quality and visualize on map using GIS technology for comprehensive spatial analysis and also decision support. We also provided the mathematical formulation of the model where we have the input, future vector definition, and then we provided the output quality categories as excellent, good, poor, and bad. And then we also provide the model function, the classification function. Now to finally, we visualize the classification result on GIS by following the formula given below. So the integrated solutions is seamlessly combining the deep learning classification with geospatial for comprehensive groundwater quality assessments and monitoring. Now the research objectives and expected outcomes. So the research objective is to develop an advanced AI model algorithm for groundwater quality classification and also integrate AI models with GIS for spatial risk analysis or spatial risk mapping. Now the expected outcome is for us to build an AI LGBM model, PSOSCN model, and then the GIS based models for enhancing the prediction accuracy and spatial analysis of the model. So we know that high accuracy classification for groundwater quality using machine learning can be achieved. Then actionable insight for policy making and sustainable water management can also be achieved. So that's the general objective that we have. to develop the models that integrating machine learning and GIS together. So the research scope, for the research scope, we look at the geographical location of the research. So Vietnam and Mekong Delta is used as a research area, while in Odisha, India, is another research location study that expand to Odisha. So we can provide a broader perspective on groundwater quality in different regions with diverse environmental factors. And then we look at theoretical and methodological way of running the research. So for theoretical frameworks and methodological approach, we integrate advanced ML and GIS mapping to classify and visualize the groundwater quality. Now, some state-of-the-art methods that are available, we look at it because we're looking at migrating from the traditional methods down into deep learning or machine learning methods of groundwater quality classification. So for traditional methods, we say that they include physical testing, chemical analysis, such as spectroscopy, microscopy, and lab protocols. So these methods are time consuming and they require significant manual effort. For machine learning methods, XGBoost, Light GBM, CADBoost, Random Forest, SVM, and ANFIS, AutoML are used for more accurate and efficient classifications of groundwater. Then for deep learning methods such as transformers, LLAMA 3.3, hybrid CNN, RNN, multimodal AI, these advanced models also allow for better performance, particularly in complex patterns recognitions and also when handling large-scale data. So this slide simply presents an overview of the traditional machine learning and the deep learning methods, showing the evolution and innovation in groundwater quality assessment. Now we'll talk about the methodology of the work. Now for the methodology, the study area, like I indicated from our scope, was Vietnam, Mekong Delta. The map on the left shows the Mekong Delta in Vietnam, an area of significant environmental and agricultural importance. Now where groundwater quality assessment is critical. And in Odisha, India, the map on the right illustrates Odisha, India, where similar groundwater quality monitoring is necessary due to the region's hydrological characteristics. So this slide introduces the study area, highlighting the geographical locations in Vietnam and in India where research was conducted. For the data sources, now Vietnam data groundwater was collected from the Ministry of Natural Resource and Environment, including some physiochemical parameters and spatial attributes. So for Odisha, the data source was collected from the Central Groundwater Board in India. So the data is from the regional groundwater quality that was collected from 2018 to 2020. And then we conduct a data pre-processing pipeline where we look at identifying and handling the missing data under the missing value analysis, and then outlier detection where we detect and remove any anomalies in the data. And then finally, we conduct the data normalizations, so the data for uniform scaling. And then the data split strategy data was split into training data, validation data, and testing data. So for the data preparation, we perform future engineering and data pre-processing. So for the missing data imputation, we use a categorical data modes and continuous data by using mean. So for future normalization and standardizations, we perform some standard numerical features to improve the model convergence, as we have provided the formula on the screen, as you can see. And then for water quality index, this is when new features were introduced based on the water quality formula for the future normalization. And We also conducted for the mean calculations, and for the standard deviation, we also provided the equations, as you can see. For the data description, we're simply explaining a few overview of the data. So number of rows in Vietnam data sets, about 2,103 and 39. For the number of columns, about 40, and we have date time columns too. There are missing values in the data set, and then in the Indian water quality data set for Odisha, we have 1,241 rows and 17 columns. And then for numeric columns, we have 14. There are no missing values in this data set. Now, we started by building a basic machine learning model pipeline that was used to build the other models. So we start by data pre-processing, and then begins the regional selections and water quality data collections. We conducted the exploratory data analysis, do the coloration analysis and detect outliers. And then we do the data pre-processing, that's cleaning and normalizing the data before we split into training, validation, and test. And then we do the model application. So we apply the machine learning models, followed by the performance evaluation and selection of the best model for the groundwater quality classification. So after that, we look at the operational efficiencies of the models, and that's built the foundation for the machine learning algorithms. Now, some of the advantages of MLs here are operational efficiency, real-time analysis, so we can have continuous monitoring capabilities with instance processing, and classification for immediate water quality management or assessment, handling of non-linear relationship. And so those are some of the advantages. Now, the DL methods for groundwater quality, such as neural networks, they are also used for classification purposes. So deep learnings, specifically neural network, are used to classify groundwater quality by learning complex patterns from the data. So it has the ability for multimodal data processing. So the models process various data types, such as maps, rainfall data, and satellites data as well. And also automated feature learning. The model can automatically learn and extract relevant features from raw data without manual intervention. And then the data workflow, simply deep learning workflow, we input the data from different sources, then which is fed into the neural network for classifications, and then the network processes the data and output a classified map showing the water quality distribution. So this is just an overview of how things are going to be. Now, this is the model that was built after the ML model. We built this model. So there are three important stages of this model, AI LGBM model. As you can see, stage 1 is the feature extraction, stage 2 is the training, and then stage 3 is the testing, results, and explanation. So in stage 1, we process the trained data. So we start by cleaning data, addressing missing values and pre-processings. And then we perform the feature selection. We selected the top K features based on mutual information score. And then we calculate the R score to rank the features and remove the ones with the lowest ranking based on the MI and R. Now the features are ranked and undesirable ones are removed. Then stage 2 is for the training. We feed the processed data into LightGBM, gradient boosting machine model, and then also perform swarm initialization strategy by initializing the population for optimization. And then the fitness functions and evaluation by evaluating the model performance using the fitness function, and then the performance output and so we produce the output after training, and then the test results where an explanation was done. So the optimized model is now optimized using the test data, and then we provide predictions and we assess the performance. For interpretability, we use Lyman Sharp for model explanation and future importance. So these slides outline the complete process from data extraction and future selection to model training, optimization, and explanation of the result of the model. Now, the second model is the hybrid PSO-SCNN model. So this slide illustrates the custom designed transformer-based RaceNet architecture for future extraction. So we start by stage 1, input data. So the model received spatial data and attributes input for future extractions, and then it's moved into the novelty layer. This layer includes the backbone future extractor, which uses also Harbison distance for embedding spatial and attributes inputs. The data is concatenated and futures are extracted. Now the next layer includes multi-head attention for effective future processing, and then the data is reshaped and the dots products of the elements are computed. And so task 4, which is task specific head, after batch normalization, the data undergoes convolutional operations, then followed by ReLU activation and batch normalization. Then we run the PSO hyperparameter tuning, which is applied to optimize the model. And then finally, stage 5 is the output classification. So that is the model performs classification after the data passes through the pooling layer, followed by the flattened layer and fully concatenated layers. So this final output is the predicted classification. So these models integrate deep learning, PSO optimization, and spatial data processing to enhance groundwater quality classification. The other model is the CNN GIS model, and this model is the one that we use to visualize the classification result on the GIS map. So step 1 is the input data and cleaning. So we conducted feature engineering, collect and clean GIS data, physiochemical data, and categorical features, as well as feature vectors. So we prepare the data for the model in step 2, which is the backbone feature extractor. We have the embedding dense layer that transforms the input data into dense vectors, and then we concatenate by combining the spatial and physiochemical data and categorical data features for further processing. And then step 3, we conducted an optimization using PSO, and the criteria for optimizations was set up in this layer. And then finally, step 4 is the classifier and output. So this is where we have the result classification, and we visualize them in a GIS application. I will quickly talk about the experimental result. So for the experimental results setup, the experiment was conducted using Python 3.9 with libraries such as Pandas, NumPy, Matplotlib, Seaborn, and Scalene. And then the training data set from Vietnam and India was used. Hyperparameter tunings and validation techniques were also used. So these slides just provide a summary of the experimental setup, highlighting the tools, the data source, and then a few methodologies that were applied. Now for the AI LGBM model execution, the formula shown represent the output prediction for a specific instance using the AI LGBM model. And this process describes how the model generates its predictions by combining the result of multiple decision trees and evaluating the errors during classification. The model training and evaluation metrics. So we look at Model training evaluation. So the classification loss is calculated using the formula that we provided in the first screen. So this measures the error between the predicted and actual outputs, helping to train the model by optimizing or by minimizing this loss. And then we have the performance evaluation accuracy. The accuracy is calculated by comparing the predicted levels to the actual levels as given in the equation. And then finally, we have interpretability, where we use the Shapley values for future, which is calculated to explain its contribution to the model's output. So this helps us to understand the importance of futures in the decision-making process. These matrices are also metrics are essentials for evaluating models' performance and also ensuring that they provide interpretable results. Now, comparing or comparison of results for the AI LGBM model. Now, the AI LGBM model outperforms the traditional methods with 94% accuracy. It has an improved interpretability. It has an improved interpretability with mutual information futures and selections, and also autoimmune. Now, the CNN in this layer also shows that F1 score is a bit higher and recalled compared to AI-LGBM, but AI-LGBM remains competitive in general classification. This is in the table 2.13, as we can see on Odisha data sets. Now, on the Vietnam data set, table 2.14, the AI-LGBM model performs similarly well, achieving a 94% accuracy, which demonstrates its consistent performance across different datasets. So the CNN model outperforms in precision and recall, but AI-LGBM also hold an edge in general classification tags. Now, the advantages for the AI-LGBM is that it's improved the accuracy by selecting key features, and it's achieved a 94% accuracy, making it effective for general classification tags. So we also conducted a comparison result for the PSOSCN and the CNN GIS model. And so the PSOSCN achieved 98.8 accuracy, 97.5 precision, and 99.5 F1 score. Now, significant improvement over traditional methods. And then the CNN GIS also achieved a 97% accuracy, 96 precision, and 97.5 F1 score. Now, the advantages are that they improve classification accuracy by optimizing the CNN model using PSO. And also we combine the PSO for hyperparameter optimization with CNN for spatial feature extraction. Now, if we look at the table 3.17, we will also look at the comparison result between the all models that was developed, that is the AI-LGBM model, the PSOSCN, and the CNN GIS model. So we can say that the PSOSCN provides 98.8 accuracy and achieves perfect recall of 100. And so that's the indication that the model really achieved and did very well as we expected it to. For result for the spatial mapping, we use the advanced geospatial analysis for environmental decision making. So we try to visualize the spatial result on map to indicates the quality or the points where water quality are shown. So we can see that on the first, by the left, classification of water quality, Vietnam national coverage, where we classify water as drinkable and not drinkable. So the red point indicates not drinkables and the green point indicates drinkable. Then we also look at groundwater quality distribution by region analysis, where we have Vietnam water quality classified as excellent, fair, good, medium, and poor. Then we also look at what Hanoi water quality analysis, that's taking one urban area detailed view to show where water is referred to as excellent, fair, good, poor, and medium. Now, these slides provide spatial visualization powered by CNN GIS mapping, which provide a clear, actionable insight for environmental decision making regarding water quality across multiple regions. So in conclusion, we say that the AI LGBM model significantly improves the accuracy of groundwater quality classification by combining mutual future information based future selection and autoimmune optimization. The models achieve an accuracy of 94%, outperforming the traditional models like logistic regression and decision trees, while the PSO-SCN model, which is a hybrid model, achieve a remarkable performance, reaching an accuracy of 98.8. This model uses particle swarm optimization to fine-tune hyperparameters and integrate spatial convolutional neural networks for better capturing spatial dependencies in groundwater quality data. The CNN GIS model combined with geographical information system for spatial mapping. The model enables effective visualization of groundwater contamination zones and offering valuable insight for real-time decision making and also resource management. And so we can say that the AI-driven models significantly improve the groundwater, groundwater quality classifications. So the key contributions of the research, we were able to optimize future selection. So we improve model efficiency by selecting only few essential water quality indices, which reduce dimensionality without compromising accuracy. We talked about spatial intelligence integration, so unique integration of spatial data with machine learning, addressing gaps in spatially aware groundwater quality assessment. We look at development of PSO-SCN model that enhance accuracy and spatial analysis using the PSO and also spatial convolutional neural network. And then we look at improved interpretability, where we use sharp and lines to enhance model transparency, allowing stakeholders to understand key factors that drives classification and prediction. And then also practical application, we provide actionable insights for groundwater pollution detection and also resource management, aiding policy decision for water sustainability. So for the practical contribution, we can say pollution detection. So early detections of groundwater contamination with improved response time can be done. GIS water mapping, detailed spatial visualization of pollution hotspots and optimized resource allocation. Real-time support, actionable insight for water managers, enabling dynamic quality management and also resource optimization. Now, the limitation of the research study, we have geographic scope, so we are limited to Vietnam and India, so data set not globally represented. And model generalization, hybrids model may not transfer effectively to other regions, and time constraints, limited time for comprehensive optimizations and validation, and also computational demands, high processing requirements for deep learning models, and incomplete or noise data may impact model performance. Now, the future research direction will look at model refinement, where we can optimize the hybrid models for enhanced performance and computational efficiency, and then real-time monitoring, develop system for continuous groundwater quality tracking and alerts, and then look at some environmental factors where we can integrate land use and additional variables to improve the model accuracy, and then climate integration, incorporating of climate data to assess long-term groundwater quality impact, and then geographical expansion, where we can apply validated models to diverse regions for broader implementation. That is the future research direction. Some thesis publications, some publications that were done within the thesis. So this slide highlights the publication resulting from the research effort, showcasing various collaborative works and paper related to groundwater quality classifications using AI models. So notably, the papers are in collaboration with other researchers, and several papers have been published on machine learning and deep learning techniques applied to water quality classifications and geospatial data analysis. Now, upcoming publication also focus on the PSOS CNN models for water quality predictions under review by Journal of Indian Society of Remote Sensing. Thank you so much. This concludes my presentations, and thank you for your attention and interest in my research on groundwater quality classification and spatial analysis. If you have any further questions or you would like to discuss the topic in more details, feel free to reach out to me. Thank you so much.